In the previous lecture, we started the discussion on the analysis of MMIC amplifiers using S parameters. So as we had said, MMIC is the transistor plus the biasing circuit, that is all packaged in the form of a chip. And what is available to us as the user is the input and output ports of that amplifier. So essentially it becomes like a two-port network which is lossy, which is non-reciprocal, and it may or may not be matched. So therefore we had actually studied something like this, that if you consider the MMIC amplifier as a black box, and at some frequency f, let us say, we are analyzing it, it has the S matrix S11, S12, S21 and S22. This is port 1, this is port 2. So what we had said was that if you assume that the wave entering is V1 plus and the wave exiting port 1 is V1 minus, then this will be V2 minus and this will be V2 plus. Now suppose we say that the amplifier has to drive some load that is connected at port 2. Some ZL is over here. So port 1 is the input port and port 2 is the output port. So what we had essentially done is to represent this entire network, including the load, in the form of a signal flow graph, where every node represents a voltage and the branch represents some coefficient like the S parameter or the reflection coefficient. So we had said that let's define the load reflection coefficient as gamma L. And if you assume that the port feed lines have characteristic impedance of Z0, then gamma L is nothing but ZL minus Z0 divided by ZL plus Z0. And in terms of the voltage waves, it is the reflected voltage from the load divided by the incident voltage from at the load. Reflected voltage is V2 plus and incident voltage is V2 minus. So the signal flow graph then would look something like this. Let's say this is V1 plus, this is V2 minus, this becomes S21, this becomes S11, and this is V1 minus, this is V2 plus, this is S12, and this is S22. And in the previous lecture, we had also shown a way to represent the load reflection coefficient, because V2 plus is nothing but gamma L times V2 minus. So therefore, we can call this branch as gamma L. So in an ideal scenario, we expect that because of the virtue of the definition of the S parameters, any input at port 1 will cause some output at port 2. So therefore, the voltage gain of this amplifier would be S21. So therefore, we call S21 as the intrinsic voltage gain. The intrinsic voltage gain of the amplifier. But after connecting some load, we cannot expect that we will always get the S21 itself as the total gain of the amplifier. So therefore, we want to know the actual voltage gain. Let's say this is AB, and we define it as the output wave divided by the input wave. So output wave is at port 2 and the input wave is at port 1. So we can use the Mason's rule to actually solve for this quantity. So we want to see the paths from V1 plus to V2 minus. There is only one path, P1, that is S21. So there is just one loop, that is this one, and the loop gain over here is S22 times gamma L. So therefore the delta of this network will be 1 minus the loop gain of the first loop, which is 1 minus S22 gamma L. Now corresponding to P1, there will be something called delta 1, which is the value of delta for all the loops that are not touching path 1. So if path 1 is here, you can see this loop is actually touching that path. So therefore the delta 1 is nothing but 1 itself. So therefore this voltage gain is actually P1 times delta 1 divided by delta. If you substitute all these values, you will get this as S21 divided by 1 minus S22 times gamma L. Now, we had defined initially that S21 is the gain that we want. And we sort of expect that any amount of load that we connect would act in a very negative way and reduce the gain of the amplifier overall, if you were to observe the output across the load. And for most cases that happens also. But those discussions are predominantly for low frequency circuits. At high frequency or RF circuits, where we are essentially denoting all the voltages and currents as waves, what we are seeing is that the voltage gain essentially comes down to something like this. It depends not just on S21, it also depends on the load reflection coefficient gamma L, and it also depends on S22. Now what is S22? S22 is the reflection coefficient looking into port 2 when all other ports are matched. So in some sense, S22 tells me about the reflection coefficient when I'm looking into the port 2 of this amplifier or port 2 of this network. Gamma L, as we know, is the load reflection coefficient. Now, what I can say is that irrespective of what the value of S21 is, since S22 and gamma L indicate reflection coefficients, their values are very likely to be less than 1 in magnitude. So normally the mod of S22 and mod of gamma L will be less than 1, that is expected. So therefore the product of these two will also have its magnitude less than 1. So 1 minus that quantity will be something which is again less than 1. So if you are dividing some quantity by a quantity that is less than 1, the net result will be something that is much more than the numerator. So what will now happen is, we know that AV is S21 divided by 1 minus S22 times gamma L. So if the mod of S22 gamma L is less than 1, then what I can say, the mod of AV will definitely be more than the mod of S21. So therefore, I had made this statement to conclude the previous lecture, saying that by having non-zero load reflection coefficient gamma L, we can actually hope to get more gain from the amplifier. And that presents to us a wonderful new door of opportunity where we can actually enhance the performance of the amplifier. But the cost is that there will definitely be some power that is reflected from the source, from the load. But that's a different issue altogether. Obviously, it is again something that we don't want. But at the same time, we want also to deliver the maximum possible power to the load, and that we can do in one of the ways by boosting the gain as much as possible. So what we discussed so far is the voltage gain. What we discussed so far is the voltage gain. But as I have mentioned this before, As we know that as far as RF is concerned, the definitions of voltage and current are rather loose because they are dependent on position as well as time. So therefore, for most RF applications, what we do is we are more concerned with things like energy and power. So whatever be the voltage at some point of time, at some point, some physical point in the circuit, we can say that irrespective of that, the power is something that is more universally defined. So let us say if I define in terms of power, let us say I have an amplifier. Let us say I have an amplifier with some input and some output, RF in and RF out, two-port network. Now let us say at some frequency, let us say at 2 gigahertz, the amplifier is able to give me a gain of 15 dB. So therefore, if I give a wave with an input power of minus 10 dBm, remember dBm is the power in dB with respect to 1 milliwatt. So therefore, the output power then would be 5 dB if source and load are matched. dBm, sorry. dB is the unit of gain and dBm is the unit of power with respect to 1 milliwatt. Now, we are able to say this because we know what the power gain is. It's given to us, it is 15 dB for an amplifier. But the question is, if I know what is the S parameters of that amplifier and what is the load, can I define the power gain in terms of those parameters? So therefore, we define for any amplifier something called as power gain or GP. Normally we use A for voltages and G for power. Voltage gain A and power gain G. So this is defined as the ratio of the power delivered to the load divided by power entering the amplifier. This is how we define. So what we are now seeing is that we are more concerned about what the load is than what the source is. We are worried only about the power that is entering the amplifier, irrespective of what the source is. But the important thing is that we are concerned with delivering power to the load. So such kind of approach is correct for what is called as power amplifiers. So as I was saying in one of the previous lectures, power amplifier is something that is used in a transmitter chain where it has to pump a certain amount of power into an antenna, which is nothing but a load. So therefore, the power gain is highly useful in the scenario of designing power amplifiers. So what we call these long terms have some symbols also. So the power delivered to the load is denoted as PL divided by Pin, where Pin is the power that is entering the amplifier. So therefore, let us again go back to our depiction of the MMIC. So since we are concerned about what is the load and what is the power entering, we are not bothered with the source. This is port 1, this is port 2, and port 2 is connected to some load, that is ZL. Some load ZL. So therefore, if you consider power entering at port 1, we call this as V1 plus, power exiting, that is again V1 minus, this is V2 minus, this is V2 plus, and obviously the load reflection coefficient is gamma L, and the line characteristic impedance is Z0. And let us say at some frequency f, the S parameters are this. The analysis will change for different frequencies. That is always to be kept in mind. So we can again depict the signal flow graph in this fashion. So let us say I define V1 plus as here, and I'll call this as 1, path gain of 1, and this is V1 minus. This also I'll call as path gain 1, because I'm going to define the network over here. And just like last time, we are going to define the load in this way. S21, S11, S22 and S12. This will be gamma L. And this is V2 minus and this is V2 plus. So therefore, if I were to now define the PL, that is the power across the load or the power delivered to the load, what would it be? It is effectively, it will be proportional to the load impedance, yes, but it will also depend on V2 minus and V2 plus. So V2 minus is what is coming to the load and V2 plus is what is getting reflected. So therefore, the power across the load will be proportional to the voltage difference or the voltages of the two waves. But as you know, the power is proportional to the squared magnitude of the voltage. So therefore, the power across the load will be the power carried by V2 minus the power carried by V2 plus. The power carried by V2 minus the power carried by V2 plus. So therefore, this will be V2 minus whole squared minus V2 plus whole squared. Notice the proportionality sign. I have not said anything about the impedance. Usually it is with respect to Z0 because V2 plus and V2 minus are already decided by ZL. Now what about P in? Remember, we are trying to derive GP, which is nothing but PL divided by P in, where P in is the power that is entering the network. The power that is entering the network would definitely depend on V1 plus and V1 minus. So the power that is being carried by the V1 plus minus the power that is carried by V1 minus, that is the power that is entering the network. So this will be proportional to mod of V1 plus square minus mod of V1 minus square. So therefore, since both are defined with respect to Z0, we can very easily take a ratio and say that GP is actually PL by P in, and directly remove the sign of proportionality and say that this is V2 minus squared minus V2 plus squared divided by V1 plus squared minus V1 minus squared. Right? So now, what I can do to simplify this is to take out V2 minus and V1 plus as common from both numerator and denominator. So if I do this, what I will get is V2 minus squared times 1 minus V2 plus by V2 minus the whole square divided by, if I now take V1 plus as common, what I will get is 1 minus V1 minus by V1 plus whole square. So what I will get now is this quantity V2 minus by V1 plus the whole square. Now V2 plus divided by V2 minus. V2 plus by V2 minus. What is it? V2 plus is the reflected voltage at the load V2 minus is the incident voltage at the load. So therefore, we have already proved over here that V2 plus is gamma L times V2 minus. So therefore, V2 plus by V2 minus is nothing but gamma L. So in the numerator, what we will get is 1 minus mod gamma L square. And in the denominator, what is V1 minus and what is V1 plus? Or rather, what is V1 minus divided by V1 plus? Well, if you look at port 1, it is V1 minus divided by V1 plus. So that is nothing but the reflection coefficient looking into port 1. And in the previous lecture, we have already given a term for this, which is gamma in. Where gamma in, we have defined is the reflection coefficient looking into the input port 1 of the amplifier, which is V1 minus divided by V1 plus. We have already defined this, and also its formula we had derived in the previous lecture. Is that fine? So, the denominator will be 1 minus mod gamma in square. One minus mod gamma in square. Now, the only unknown that is remaining is V2 minus by V1 plus. But why should that be an unknown? We've already defined it. We already derived that is nothing but the voltage gain. V2 minus divided by V1 plus, which is this quantity. So therefore, we can replace this quantity with the voltage gain quantity that we have derived. So here that will be nothing but divided by mod S21 square divided by 1 minus S22 gamma L mod the whole square times 1 minus gamma L square divided by 1 minus gamma in square. So now we've got this expression, which is in terms of the quantities which we are mostly familiar with. Let us write this in a slightly different way. Since there are so many terms, we will write them as some terms in the source side, some terms for the MMIC, and some terms for the load side. So what we will do is we will represent GP as some source side terms times the MMIC terms times the load side terms. So the source side term was 1 minus mod gamma in square. So what we will do is we will write it over here. The only term that is corresponding to the MMIC is the mod of S21 square. And the load side term, there were two. One for gamma L, the other one was using S21 gamma L. So just by rearranging the terms, what we get is 1 minus mod gamma L square divided by mod of 1 minus S22 gamma L whole square. So essentially, if you notice, it is nothing but rewriting the expression that we had derived in slightly different order, which should not make any major difference. The reason for doing so is because we would just like to see the terms that are being contributed by the, or rather denoted by the input side or the source side terms, S21 which corresponds to the MMIC, and the load side terms or the output side terms which are these. Of course, as you notice, this is not completely independent output. It also depends on the MMIC. So although it's not foolproof, it is something that is very important. Now, all of these we know. S21 we know, S22 we know, gamma L we know. Only thing that we don't know is gamma in. But again, that should not be difficult. In the previous lecture, we had derived an expression for gamma in. using signal flow graph. But gamma in is nothing but this V1 minus divided by V1 plus, and that is, if you recall, the expression was something like this. It is something like this. So, all said and done, what we are now seeing is that this GP, it depends on this intrinsic gain S21 of the MMIC. It depends on the load reflection coefficient. It depends on the reflection coefficient of the MMIC looking from the load side. And it also depends on gamma in. So, gamma in, as you know, is the reflection coefficient looking into the input of the amplifier. So, therefore, it depends on the load, not on the source. As you can see over here, depends on the load, not the source. There is no question of gamma S or the reflection coefficient at the source side. So therefore, this is useful for power amplifiers. Or also called as PS. Now, so far we have defined what is the power gain. At the same time, it is important to note that this is not the only possible gain expression that an MMIC can have. Why? Because we ourselves said that the power gain is more load centric. Load centric design, where we are not caring about the source. So there could be also some gains, or we can model the gain in such a way that we focus on the source more than the load. Those are called as source centric designs, where irrespective of the load, it is the source side which is more important. And such kind of amplifiers where the source side is more important than the load side, they are called as low noise amplifiers or LNAs. And as we have discussed briefly in one of the previous lectures, while the power amplifier forms the last block in the transmitter chain, the low noise amplifier forms the first block in the receiver chain. So therefore, for low noise amplifiers, the source side is more important, as the load side is usually a matched load. There could also be a gain parameter where both source and load are important, both source side and load side. So let us now define two more gain expressions. So just like how we defined GP, the second one is called as GT, defined as the transducer gain. The transducer gain of the amplifier. Because I am writing G, they are essentially denoting power gains, which is equal to PL divided by P AVS. Now PL means the power delivered to the load. Now what is PAVS? PAVS is the maximum power that is available from the source. The maximum power that is available from the source. This is called as transducer gain. Likewise, there is another gain called GA, which is called as the available gain of the amplifier. AMP superscript R is also a short form for amplifier. Now this is defined as PAVA divided by PAVS. PAVS is the same as before. PAVS is the maximum power available from the source, whereas PAVA is the maximum power available from the amplifier output. So these are two quantities which are very important. So what we are seeing is that for GT and GA, the common term in the denominator is what is called as AVS or PAVS, or what is the maximum power that is available from the source. So the maximum power available from the source comes as a consequence of the maximum power transfer theorem, where the source, including the source impedance, which is usually non-zero, will be able to deliver the maximum possible power from itself. If and only if the load seen by the source is equal to the complex conjugate of its source impedance, which is internal. So if I talk about PAVS, that is maximum power available from the source, and source here means the RF source, not the DC source, obviously, because we are talking of RF power gain. Now suppose there is a source over here which has an internal source impedance, that is ZS. Now these are the terminals that are available to us. We don't have access to this terminal, kind of like a battery. Now let us say the amplifier is connected to some ZL, some load impedance ZL. It's connected to some impedance ZL. Now the maximum power will be available if and only if ZL will be equal to the complex conjugate of Zs. This is the maximum power transfer theorem. Right? So the question is, can we find out some expression for the maximum power from the source? So let us say this voltage is Vs. This voltage is Vs. So what will happen essentially is that when we are connecting a load to the source, definitely there will be some voltage drop across Zs, or there could also be some reflection. So let us draw this in a slightly different way. Let's say this is Vs, this is Zs, and let us say there is a small transmission line which is connecting the source to the load. Let's say that that transmission line has some characteristic impedance Z0. Characteristic impedance Z0. So how can we analyze this? So since it's a load that is connected to the terminals of the source that are available to the outside world. Let us say that the source EMF, so to speak, is something over here, that is Vs. Because over here, so far there is no concept of Zs. Now, after passing through Zs, this undergoes some voltage drop and the wave comes over here to the load. So from the source side, we are not talking about the source as a frame of reference. There is a wave that is being generated by this source and coming to the load. So therefore, let us call this as the outgoing wave. Let us call this as the outgoing wave. Now, from the source end, rather from the load end, what we are seeing. Now, the load is the crux of the system. The source, we cannot change anything. But we can definitely do something about the load, where we can try to ensure that the ZL will be the complex conjugate of Zs. So therefore, the power literally and figuratively lies with ZL. And we say that there is a wave that is entering ZL from the source. And let us call this as the generator voltage, because it is kind of like the terminal voltage from the, if this is the EMF, this is the terminal voltage. Therefore, let us call this as Vg plus. Now what will happen? There will be some reflection at the load and the reflected voltage will start traveling back to the source. So therefore, let us call this as Vg minus. Vg plus and Vg minus. Now, when this Vg minus comes here, the source has zero impedance, but this one, Zs, has some impedance. So therefore, there will be some reflection. And what will happen if you notice, there is no other impedance seen by Vg minus except Zs before it comes to Vg plus. There is no other impedance that is seen. So therefore, the Vg plus will also depend on the source reflection coefficient gamma s. So now therefore, let us define two quantities. Gamma L, which is the load reflection coefficient, that is ZL minus Z0 divided by ZL plus Z0. And the source reflection coefficient gamma s is Zs minus Z0 divided by Zs plus Z0. So therefore, the Vs, I can now again represent this as a signal flow graph. Let us say this point is my Vs, the source voltage. It comes to this point where the voltage is Vg plus. Now, the Vg minus is over here. It passes through ZL. Therefore, the load reflection coefficient will be this branch, gamma L. Now, as I said, Vg minus also undergoes a reflection at the source and becomes Vg plus. So therefore, there will be one more branch. We will call this as gamma S. This is the signal flow graph. This will be one. So it's like saying the reflected wave is going, at the same time the source is also on. So these two will effectively add up over here. And that is what is happening in the signal flow graph. The reflected voltage is also coming and the source voltage is also coming over here. You can correlate this discussion with the one we had quite a few lectures ago when we were discussing about the transient analysis of transmission lines. So we can write an expression for Vg plus, which is actually the sum of these two branches, that is nothing but Vs plus gamma s times Vg minus. At the same time, I can write an expression for Vg minus again using Vg plus. So this is Vs plus gamma s times Vg minus is gamma L times Vg plus. Now, if we were to use the maximum power transfer theorem, if we now put ZL as the complex conjugate of ZS, then what will happen? Then gamma L will also be the complex conjugate of gamma S. So therefore, we can substitute this in the Vg plus expression, which gives us Vg plus is equal to Vs plus gamma S into gamma S conjugate times Vg plus. So gamma S and gamma S conjugate would give you what? The mod of gamma S square. So I can get an expression for Vg plus in terms of Vs. So that means Vg plus will be Vs divided by 1 minus mod gamma S square. What about Vg minus? So we've got an expression for Vg plus, and Vg minus we already know is gamma L times Vg plus, and we now know gamma L is nothing but gamma S conjugate, that is gamma S conjugate times Vg plus. Now we know what is Vg plus, gamma S conjugate times Vs, this thing, divided by 1 minus mod gamma S square. So therefore, the PAVS, the maximum power available from the source, will be the difference between the power carried by Vg plus and the power carried by Vg minus. So this will be proportional to this. And you can very easily substitute and see that it is nothing but minus I hope this is correct. Yes, so that is nothing but, if you take this, you will have 1 minus gamma square in the numerator, and in the denominator you have 1 minus gamma square the whole square, and there will be cancellation, which will make it Vs mod square divided by 1 minus mod gamma S square. This is the maximum power available from the source. With this, you can now go over and define what is GT, or the transducer gain. As we defined, GT is nothing but the power delivered to the load divided by the maximum power available from the source. We already know how to derive PL, and we have derived PAVS. So it's a no-brainer to solve now, and you will get that GT will now be this expression. You can work it out yourself. I'm leaving this as an exercise. One minus gamma in times gamma S the whole square times mod of S21 square times 1 minus mod gamma L square divided by 1 minus S22 gamma L the whole square. This is what is GT. You can notice that some of the terms are already familiar. from the previous discussion on GP. So it's just an extension of GP. Now what about the available gain? GA, that we have defined as PAVA divided by PAVS. PAVS we know, we have defined it just a while back. PAVA is the maximum power that is available from the amplifier. So now it is very similar to PAVS, except it is now on the output side. So let us say there's a source over here, some ZS, and there is some load at port 2, that is ZL. This is my amplifier. So over here there will be some gamma L. The amplifier, now if you assume that this entire part, the source and the amplifier is one big source, the amplifier will be able to give you maximum power, again using the maximum power transfer theorem. So if you are saying that looking into the amplifier output, you are seeing an impedance called Z out or reflection coefficient gamma out, the maximum power will happen when ZL is equal to the complex conjugate of the output impedance of the amplifier, or in other words, gamma L should be equal to the complex conjugate of gamma out. Now notice one thing, for GT it depends on both the source impedance as well as the load impedance. So just like how power gain depended on only the load side, GT depends on both source side and load side because of gamma S and gamma L. So likewise, if you apply this into GA, you can derive that GA is nothing but this quantity. I leave this again to you as an exercise, which should not be very, very difficult. So what you will see now, GA depends only on the source parameter. So therefore this is source centric. Gamma out is the opposite of gamma in. So the formula is also kind of the opposite of the formula for gamma in. So gamma out using signal flow graph, you can show that it will depend on ZS, and that is nothing but S22 plus S12 S21 gamma S divided by 1 minus S11 gamma S. And notice, if you recall, the gamma in was something like this, S11 plus S12 S21 gamma L divided by 1 minus S22 gamma L. So notice how the two are kind of converses of each other. So in this particular lecture, we discussed about the voltage gain of an MMIC, followed by the power gains. We talked about three kinds of power gains. One is called as the actual power gain GP, which is load centric. We talked about the available gain, which is source centric, and we talked about the transducer gain GT, which depends on both source and load. So we shall continue from this point onwards. We will do more with these gain expressions, but from the next lecture onwards. Thank you.